Hello and welcome to my poster presentation. My name is Hamed Haghshenas and this poster presentation is about time-optimal path tracking problem for cooperative robotic manipulators. Path tracking is the second stage of the so-called decoupled approach, an approach for solving motion planning problems. And it concerns itself with determining the trajectory along a prescribed geometric path while taking robot dynamics and actuator constraints into account. We have studied the time-optimal path tracking problem for a team of cooperating manipulators. We consider a scenario where an object is rigidly grasped by multiple manipulators, and the objective is to minimize the traversal time required to move the object with the desired orientation along the prescribed geometric path. We have shown that this problem can be cast as a convex optimization problem and subsequently as a second-order Coombe program. A fundamental property of convex optimization problems is that any locally optimal solution is also a globally optimal one. Also, by formulating a problem as a second-order Coombe program, it can be solved reliably and efficiently using the dedicated solvers for this type of problems. The procedure for formulating the problem as a convex problem involves finding the coupled dynamics between the object and manipulators and writing it in terms of the first and the second order time derivatives of the path coordinate, which are later introduced as optimization variables. As a result of this change of variables, the coupled dynamics, which enters as constraints in the optimization problem, becomes the linear in optimization variables. The second part of the poster is devoted to finding load distributions that are free of internal forces. In general, there exists an infinite number of forces exerted by the end effectors at the grasping point that results in the same desired force on the object. Normally, this redundancy is resolved using a load distribution strategy and by means of a pseudo inverse, which allocates suitable torque and force set points to the manipulators. The resulting interaction forces are decomposed into motion-inducing and internal forces. So internal forces are squeezing or pulling forces that do not contribute to the motion of the object. While a certain amount of such forces can be useful in some cases, in general, they must be avoided to prevent object damage and unnecessary effort of the manipulators. We have proposed a new approach to obtain internal force-free distributions. The proposed approach results in a new pseudo-inverse parameterized by coefficients that have the meaning of inertial parameters of some part of the object. The freedom in the choice of the parameters of the pseudo-inverse allows to assign different loads to the manipulators, and this can be exploited to account for the differences in the power capabilities of the manipulators. The results are further explored for scenarios where the object is three-dimensional and convex and has uniform mass density. This concludes the presentations, and thank you for listening.